Now we will discuss about the oxidation number. Oxidation number and oxidation state. It is an imaginary or apparent charge developed over atom of an element when it goes from its elemental free state to combined state in molecule. It means when atom of an element goes into molecule of compound, then atom of an element attain a apparent or imaginary charge in molecule. Imaginary charge on atom which present in molecule of compound. Before conversion, pure atom of an element has zero oxidation number, or we can say that oxidation number is equal to 0. So we can say that atom present in element has oxidation number is equal to 0, but when atom present in molecule of compound, it doesn't has oxidation number is equal to 0. Means oxidation number of atom is not equal to 0 in its compound state, and it attain any charge that is called imaginary charge or apparent charge. Now there is a need to find out the value of apparent charge or value of imaginary charge. So we will discuss about the rules governing oxidation number, that is known as imaginary charge. This imaginary charge is known as oxidation number. So we will discuss about the rules governing oxidation number. How can we find out the oxidation number of any atom present in molecule? So firstly, for fluorine atom, as we know, the electronegativity of fluorine atom is highest in among all the elements. Fluorine has highest electronegativity among all elements. So when fluorine attach with any atom, now we consider A. When fluorine attach with any atom, it attract the bond pair of electron. This one is electron of A and this one is electron of fluorine, and it attracts the bond pair of electron. So fluorine acquires a partial negative charge and A acquire a partial positive charge. So we can consider oxidation number of fluorine is equal to -1. So we can say that there is not a significance of delta negative. It is wrong. So according to rule, we always consider oxidation number of fluorine is equal to -1 in any compound. So this is a universal rule that oxidation number of chlorine is always -1 in every case. Now for oxygen atom, in general and as well as in its oxides, oxygen atom has oxidation number is equal to -2. in general or in its oxides. Oxidation number of oxygen is equal to minus 2. For example, in sodium oxide, that is Na2O, oxidation number of oxygen is equal to minus 2. As same as in magnesium oxide, oxidation number of oxygen is equal to minus 2. And in many more examples like potassium oxide, calcium oxide, ferrous oxide, zinc oxide, etc. Oxidation number of oxygen is always minus 2. But in some other cases, oxidation number of oxygen is not minus 2. So for example, in some other cases, in peroxides, oxidation number of oxygen is equal to minus 1. As we represent oxide by O, single bond O, and each atom of oxygen contains one negative charge, so we can say that here oxygen has minus 1 charge, and here also one atom of oxygen has minus 1 charge, because electronegativity of oxygen in both case is equal. So the bonded pair of electron is always exactly between oxygen and oxygen atom. So it doesn't acquire any partial charge. So we can say that each atom in peroxide, each oxygen atom in peroxide acquires a one negative charge. So the oxidation number of oxygen in peroxide is always equal to minus 1. We can take an example just as in case of sodium peroxide, that is Na2O2. Oxidation number of oxygen is equal to minus 1. And in case of hydrogen peroxide, that is H2O2, oxidation number of oxygen is equal to minus 1. So we can say that oxidation number of oxygen in peroxide is always equal to minus 1. In case of superoxide, oxidation number of oxygen is equal to minus half. Superoxide can be represented by O2 minus 1, while peroxide can be represented by O2 2 minus. So we can calculate the imaginary charge or oxidation number of superoxide and peroxide by their formula, because according to formula, peroxide, that is O2 minus, contains two oxygen atom with one negative charge, one negative charge. So we can say that each oxygen atom will contain is equal to minus 1 upon 2 charge, because two atom contains one negative charge, so each atom or one single atom of oxygen will contain minus half charge according to formula. And in case of peroxide, we discussed before, according to its formula, O2 2 minus, it contains two oxygen atom and charge is equal to minus 2 and minus 2 charge. So we can say that two oxygen atom contain minus 2 charge, so one oxygen atom will contain is equal to -2 divided by 2 is equal to -1 charge. So we can say that oxidation number of peroxide, oxidation number of oxygen in peroxide is equal to -1, and in case of superoxide it will be -half. Now we can take an example of superoxide. Now we can take example of superoxide. It is potassium superoxide, that is KO2. In this case, oxidation number of oxygen is equal to -half. And next case, in case of ozonide, and we can represent ozonide by O3 minus. According to this formula, ozonide contains 3 oxygen atoms and contains -1 negative charge. So one atom of oxygen will contain is equal to -1 upon 3 charge. So we can say that in ozonide each oxygen atom contains -1 by 3 charge. So we can say that oxidation number of oxygen in ozonide, that is O3 minus, is equal to -1 by 3. Now we can take example of ozonide, potassium ozonide, that is KO3. In potassium ozonide, oxidation number of oxygen is equal to -1 by. Now for hydrogen atom. Hydrogen atom can acquire a +1 or -1 OS. Either maybe +1 or -1 oxidation number. When hydrogen attach with non-metals such as chlorine, fluorine, bromine, sulfur, oxygen, etc., it acquire a +1 OS. In this case, it has +1 oxidation number or oxidation. We can consider it by example of HCl or HF, which we have been discussed before. In this case, fluorine has high electronegativity than hydrogen, so it attracts the bond pair of electron strongly, so it acquires a partial negative charge, and hydrogen acquire a partial positive charge. And we can't consider partial charge, we always consider full or complete charge. So according to this, hydrogen has +1 OS and fluorine has -1 OS. In the same case, chlorine has a high electronegativity compared to hydrogen, so it acquires a partial negative charge, and hydrogen acquire a partial positive charge. So according to this, OS of or ON, oxidation number of hydrogen, is equal to +1, and oxidation number of chlorine is equal to -1. But when hydrogen attach with metals such as sodium, potassium, magnesium, etc., it acquires a -1 oxidation number or oxidation state. For example, in case of sodium hydride NaH, that is sodium hydride. In this case, sodium has plus 1 OS and hydrogen has minus 1 OS, because in sodium and hydrogen, sodium has more electropositivity, or we can say that sodium has a more electropositive atom than hydrogen. So it gives its electron to hydrogen and acquire a plus charge, and by gaining of single electron, hydrogen acquire a minus 1 charge. So according to this, hydrogen has minus 1 charge in this hydride or this sodium hydride. So we can say that its OS or ON will be minus 1 and oxidation number of sodium will be plus 1. And same example in case of magnesium hydride, that is Mg2 magnesium hydride. When hydrogen acquire a minus charge, then it is known as hydride. So we can say that in hydride form it has minus 1 OS. So we can mention it for hydride. OS of hydrogen is always minus 1. In case of magnesium hydride, hydrogen also has a minus 1 charge, or we can say that oxidation number of hydrogen in magnesium hydride is always minus 1. We can consider it by magnesium donates its 2 electron, it acquire a plus 2 charge, and here 2 atom of hydrogen gain single electron. So we can say that each hydrogen gain a single electron and attain a negative charge. So each atom has a single negative charge, so we can say that oxidation number of hydrogen in this case will be is equal to minus, and the OS or ON oxidation number of magnesium will be is equal to plus 2. Next, in case of metal, first for alkali metals, that is metals present in first group of periodic table, or we can specify first A group of periodic table, that is lithium, sodium, potassium, rubidium, cesium and francium. These metals have oxidation number is equal to plus 1 in its compound form, but in elemental state it has OS is equal to 0. So we can say that in elemental state or in free state, oxidation number of alkali metal is equal to 0, but in its compound state it has always plus 1 charge. So we can say that oxidation number in case of its compound is equal to plus 1. Second, for alkaline earth which are present in second A group of periodic table, that is beryllium, magnesium, calcium, strontium, barium and radium. For these metal, oxidation number is always equal to plus in its compound state, or we can say that in its compound. So we can take an example in sodium oxide, that is Na2O. Oxidation number of sodium is equal to plus 1 because sodium is a alkali metals. But in case of magnesium oxide, that is MgO. Oxidation number of magnesium is equal to plus 2 because magnesium is a alkaline earth metal. So we can say that in case of alkali metals, the oxidation number or oxidation state of alkali metals is equal to plus 1, and for alkaline earth metal oxidation number is equal to plus 2 in its compound form. And the third, for aluminium, oxidation number is equal to plus 3 always. For example, in case of aluminium chloride, aluminium oxide, aluminium sulfate, etc., oxidation number of aluminium is always equal to plus 3. And for other metals which have a variable valencies, we can calculate their values by following concept, because some metals show the variable valencies, so there is a need to calculate their valencies by some basic concepts. First, oxidation number of an element in its free state or in allotropic form is always equal to 0. Oxidation number of an element in free state or in allotropic forms is always is equal to 0. For example, in case of O2, that is elemental form of oxygen, and 2H2P4, that is a molecule of phosphorus in its elemental form, O3, that is a molecule of ozone in its elemental form, acid, that is a molecule of sulfur in its elemental form. So in all of these cases, oxidation number will be equal to 0. We can prove it by, in case of oxygen, 2 oxygen attached with double bond, as oxygen and oxygen has the same electronegativity, so the pair of electrons is always exactly between them, so there is a no shifting of electron, so there is not a charge on any atom. So we can say that oxidation number of this oxygen is 0, and also for this is equal to 0. So we can say that oxidation number of oxygen is 0, and in all of these cases there is a same atom present in every molecule, or we can say that all of them are homoatomic molecules. So for homoatomic molecules, the oxidation number of any atom is always equal to 0. Now second rule, sum of the oxidation number of atoms of all elements in a molecule is always is equal to 0. For example, in HF, oxidation number of fluorine is equal to -1, and oxidation number of hydrogen is equal to +1, as we discussed before. So sum of oxidation number is equal to -1, that is a oxidation number of fluorine, plus 1, that is the oxidation number of hydrogen, and it will be equal to 0. Now in case of H2, oxidation number of hydrogen is equal to +1 because hydrogen attached with non-metal. As we discussed before, when hydrogen attached with non-metal, it attain a +1 oxidation number. But there is 2 hydrogen atom present in H2, so we can say that oxidation number or sum of oxidation number of 2 hydrogen atom is equal to +1 into 2 is equal to plus. Now oxidation number of oxygen is equal to -2 because oxygen present in water as a oxide form. So sum of oxidation number of all atoms present in molecule is equal to +2 for hydrogen plus -2 for oxygen, and it will be equal to 0. Now third rule, sum of oxidation number of atoms of all elements present in an ion is always equal to the charge on the ion. Now we can take an example in sulfate ion, that is SO4 2 minus. Oxidation number of sulfur is equal to +6. Oxidation number of oxygen is equal to -2. Sum of oxidation number of 4 oxygen will be equal to -2 into 4 is equal to -8. So sum of oxidation number of all atoms is equal to -6 for sulfur atom plus -8 plus 6 for sulfur atom and -8 for 4 oxygen atom, and it will be -2, and that is a charge present on sulfate ion. So we can say that sum of oxidation number of all atom present in ion is always equal to charge present on it. Now we can calculate the charge or oxidation number of any atom by above three rules. Now we can take an example for this calculation of oxidation number of an atom present in any molecule. For example, in Na2S2O3, if we want to find out the oxidation number of sulfur, we can use the above rules. Now oxidation number of sodium is equal to +1 because sodium is alkali metals. As we know, the alkali metal has a OS or oxidation number is equal to +1, and oxidation number of oxygen is equal to -2. And let me consider now let me consider oxidation number of sulfur is equal to I. According to above rule, we know the sum of all atoms present in molecule, sum of oxidation number of all atoms present in molecule is always equal to 0. So we can put the value of oxidation number of different elements according to formula Na2S2O3. Oxidation number of sodium is equal to +1, and here 2 atom of sodium present, so we can multiply it by 2, plus oxidation number of sulfur is equal to X, and we can multiply it by 2 because 2 sulfur atom present in this molecule, plus oxidation number of oxygen is equal to -2, and we can multiply it by 3 because the 3 atom present in this oxygen present in this molecule. Now we can calculate it. +1 into 2 is equal to +2 plus 2x, 3 into 2 is equal to -6. And according to rule, we know that the sum of oxidation number of all elements present in molecule is always equal to 0. We can equate it is equal to 0, and we can write it 2x minus 4 is equal to 0, 2x equal to +4, and x equal to +4 divided by 2 is equal to +2. So we can say that oxidation number of sulfur is equal to +2 in sodium thiosulfur. Now we can take another example in H2SO. We have to find out the oxidation number of sulfur. Now we can consider oxidation number of hydrogen is equal to +1. Oxidation number of oxygen is equal to -2, and we can consider oxidation number of sulfur is equal to X. Now according to formula, that is H2SO4, oxidation number of hydrogen is equal to +1, and we can multiply it by 2 because here 2 atom of hydrogen present here, and plus oxidation number of sulfur is equal to X. We can multiply it by 1 because 1 atom of sulfur present here, plus oxidation number of oxygen is equal to -2, and we can multiply it by 4 because 4 atom of oxygen present here, and we can equate is equal to 0 because total charge on H2SO4 molecule is equal to 0, or we can say that it is a molecule, and for a molecule sum of OS is always equal to 0, and it will be 2 plus x minus 8 is equal to 0, x minus 6 equal to 0, x equal to plus 6. We can say that the OX oxidation number or oxidation of state of sulfur is equal to +6 in H2SO4. In KMnO4, we can calculate the OS of manganese. Oxidation number or oxidation state of potassium is equal to +1 because it is alkali metals. Oxidation number of oxygen is equal to -2, and we consider oxidation number, and we can consider oxidation number of manganese is equal to X. Now according to formula KMnO4, oxidation number of potassium is equal to +1, and we can multiply it by 1 because 1 atom of potassium present here, and oxidation number of manganese is equal to X according to consideration, and we can multiply it by 1 because 1 atom of manganese present here, and the oxidation number of oxygen is equal to -2, and we can multiply it by 4 because 4 atom of oxygen present here, and we can equate it is equal to 0 because the sum of oxidation number of all elements present in molecule is always equal to 0, and it will be 1 plus x minus 8 is equal to 0 is equal to x minus 7 is equal to 0, and x equal to plus 7. So we can say that in KMnO4, that is a potassium permanganate, oxidation state of manganese is equal to +7.